I had a fun little project this weekend where I took one of my CH32V006 boards and I just took a little coil of wire and decided to see if I could measure inductance. And this is just measuring inductance using some of the built-in stuff with the CH32V006. Now, there are common ways to measure inductance, such as things like being able to use a frequency counter or something like that. But I decided to see if I could use it a little bit more of a creative way. To cut to the chase, though, I just wanted to show what some of these different things look like. So if I take in like a piece of transformer ferrite for a high-frequency transformer, we can see that it greatly induces the inductance. But if we take something that's like aluminum from an aluminum circuit board, it reduces the inductance of the system. And there's lots of other materials that have other interesting properties surrounding this. So you can see most of the metals in here will reduce it. But there are other materials, like this pair of clips here. For some reason, interestingly, it causes the waveforms to actually pinch together. Now, you might be wondering, if I'm measuring inductance, what are all of these waveforms? Why are there so many different waveforms? And we'll go into that in a minute. This is using one of my new tricks. This trick is scheduled I/O, and I've done things like this in the past with my little SAO for the MagFest badge, where I was using DMA to drive an array. But in this one, it's a little bit more generic. So now what I have is I have it set up where you can schedule I/O operations to happen. So you could say at a certain time, output this value to this port, and this value to this port. And you can set all of these up and you can say, go run the scheduled operation. And there's different variations of it, ones where you can read and write arbitrarily, ones that will just read and write arbitrarily from anywhere with specific times, and just at a specific timing increment for all of the values, read from a certain place and write to others. And using these primitives, we're able to actually control something pretty neat. So I'm going to go over to the projects folder here, and a new one, the inductance tester. So for the inductance tester, what I've done is I've set up the ADC to start sampling, and then what I'll do is I'll turn on a given pin. I'll turn on the pin that's associated with this side of the coil right here. So this is PD2. And so that pin turns on, and we're set up to measure that pin as well. We're set up to receive and see what's on that pin at a given time afterwards, and then we turn the pin back off after these specific times. Now, one of the fun things is we can go through and in increments of 1/48 millionth of a second, we can sample at different times. So while we're not sampling at 48 megahertz, we're able to take a snapshot where we control the time of that sample to within 1/48 millionth of a second. What we can see here is we can see that what I've decided to do was sample many times, 32 times, and for each one of the 32 times, I wanted to be able to, in the order, start sampling. It happens around here. The ADC opens up the gate sometime around here, and then we turn the I/O back off. Editor CNLore here. After showing the video to a couple of people, they pointed out that it's probably better to visualize the time domain graph in this way instead of the other way. So this is kind of showing a faded view of where the line was. And we can see very clearly sort of like how inserting and removing these has the effect on the time. And the idea is that the time starts over here on this side, and we bump it up, and then what happens is the inductor saturates, and then eventually it's just DC resistance across the inductor. And if we put something in that can take in more energy, it will. Versus if we have something like a quarter, it kind of mutes it down. And just so you guys see what this looks like on this mode, this is what it looks like with a pair of dikes. So I don't really know why it changes what looks like a much longer tail, but yeah. So this is just a different way of seeing it. And what I mean by opens up the gate is there's a mux internal to the ADC. And that mux will then open for a short time for the ADC capacitor to be charged and be able to actually start sampling and measuring the signal. So what'll happen is we're able to, say, start at different times back here so that the gate will close at various points here so we can measure the exact voltage at different points along this arc. And so what we've done is now at each different point along the arc, so yellow is the furthest point this way, and then blue, and then orange, and then purple, and then on down. Using these, they're able to sample at different points. And while it's very difficult to actually see any kind of change in the shape of that curve based off of inductance, the precision on the 006 allows us to see very clearly changes with the inductance. So we put like a little coin here and we can see it pulls it down. Yeah, so the idea there is that by measuring those specific places, we can get a very good idea of what the value is. Now, I am oversampling, and so let's see what that looks like if we do no oversampling. So we're just going to do a single sample each, which means it'll go a little bit faster, but it's not just going to go a little bit faster. It's going to go, because I'm actually debug printfing it, so it's going to be about the same speed that you see the data come through. But now it's a lot noisier. You can see a lot more fuzz in the signal. Now it's still the same type of signal. It's still doing roughly the same kind of thing. But it's a lot furrier, I guess you could say. So the signal now is coming through da-da-da-da. Now there's a fun thing. On these little CH32V006 boards I have, there's actually a little crystal on them. And that crystal will help us make it so the timing is more precise. A lot of the error inside of an ADC is actually due to the crystal's ability to be very precisely timed. In addition, the time that we're able to measure the point on the curve is very much controlled by how precise our clock is. So what I'm going to do is I'm going to go into Fun Config, and I'm going to say use HSC. So that's the external oscillator, and we're going to rebuild everything and run it. So now, even though it's only doing a single sample, you can see that it is way less noisier and able to come through with much clearer signals. So let's see here, positioned, and so you can see it's very, very clear now that we have it. Now there are a few interesting points to note. One of them is it looks like the ADC in the 006 has some issues. So if we take a look at the kind of like teal line here, as we approach a specific code value that is divisible by 512, we end up having this strange behavior where there's sort of like a discontinuity, and I don't really know what causes that. I don't really know what's there, but I do notice that if we oversample, that does seem to go away for the most part. I know it can't go away completely, but it goes away for the most part. So let's go back to oversampling, and this is now with the crystal, so it's going to be super duper quiet. But you can see now the line there with the cyan. Teal, I guess the teal line is pretty darn quiet. There's really no discontinuity when I'm kind of getting it right near one of those values that cause problems. One of the things that the time domain view reminded me of was this Tektronix training video from the 1950s or 40s or something that showed transmission lines. And I was wondering, could I do something like that? But the only thing was I would need some absolutely insane roll of crazy coax cable, which sure enough, I just emailed some people at work, and turns out somebody purchased one a while ago for some reason, and I decided, why not give this a shot? So I decided to take a little UIA Arduino, this is from Yuki here, and hook it up and run the same firmware, extend it out some, and make it so that I send a little pulse instead of just driving it high, and then see what happens over time. And so right now it's not connected to anything, so you just see the pulse. But if I plug it in to the coax cable here, then all of a sudden you'll see that this now reflects. And what's actually going on here is the signal is being generated here. It's going down the coax cable, back and forth and back and forth, and it's hitting this open end right here and reflecting back. Now here's the neat part. When you do this with a coax cable like this, and we have a reflection, if it's open on the end, the reflection that's coming back is positive. If we short this out, so I take this right here, I'm going to just pinch that right there, you can see that the reflected signal is actually going to now reflect back in a negative way. It's kind of hard for me to keep my hand there, but you can see that it's a negative reflection. And if we instead then go and we take this is a little 51 ohm resistor because it's 50 ohm characteristic impedance coax cable. If we apply a resistor to the end, it completely negates the reflected signal. And that's why it's important to always terminate your signals. Now, one of the other things that's kind of interesting to see here is we can actually see both the signal and the reflection, and we'd be able to measure the length of the cable based on the velocity factor. But we also see these other reflections, and what's actually happening is the signal is coming out of here, going down the cable, bouncing off this end, coming back, and bouncing off this end and going back and forth and back and forth. And that's what those continued pulses are. But what we can actually do is we can take a little extension right here and plug it in, and we can see that now it's almost completely gone. It's still a little bit, but that's because I don't quite know the right value to match the impedance of the input to the CH32V06, but it's almost completely gone. But yeah, let's now go take a moment and say, based on this, how long is this cable? So what we're going to do is we're going to take the capture here, and I'm going to go start at, I guess it's about the 50th percentile, so right there, going to right there to, I don't know, maybe about here, and we'll just see how this works out. So what I'm going to do is I'm going to start by counting the number of 1/48 millionths of a second from here to here. It's actually a little bit less than 59. Maybe 58.5. That's 58.5 48 millionths of a second. So now what we're going to do is we're going to convert that into microseconds. So that's going to be over 48. And then what I'm going to do is we're going to go take these microseconds and convert them into feet. And so what we do is we take 9.836. It's 1198.76. It should be a 500-foot roll, but it is there and back, so it has to go down the cable, turn around, and return. But that's still 1,000. Why are we getting 1198.76? And the answer is something called a velocity factor. So if we take a look at the data sheet for the cable, there's a thing, the velocity percent, and that's 85%. And so that means that the speed of light is actually 85% slower. So what we'll do is divide this by 0.8, or sorry, take this and we will multiply it by 0.85. And that will give us 1018 feet. I don't actually know how long the cable is, but if we take it divided by 2, 509 feet total. I don't know. I think that that's pretty close to the length that the cable should be. certainly within the margin of error within the increments that we're working with here. This is kind of a toy problem right here that we did with just a cable going here and back and then seeing that it wasn't terminated right. But this is used in real life for things to try to identify where in a cable there's a problem. So if you have like a long line, like back in the days of DSL, and there was a problem, like a cut in the cable or a short to ground, like where the cable shorted out, you would actually see these reflections going in at different points in the cable. And by doing this, you would be able to identify where in the cable there was a break. So I dare say we might have created with this CH32V06, a little 15-cent microcontroller, or 12-cent, the world's cheapest time domain reflectometer or sampling scope. I'm not really sure what to call this thing. This is a fun little project you can do with one of these little CH32V06 dev boards, and just about any dev board, because all it takes is an ADC pin, because the same ADC pin can be used both for driving the line high and low for measuring inductance. Yeah, this was a fun little project. One of the other things I guess I should mention that this got me to do was work on this little tiny tool here called DynGraph, which is part of my my useful commands repository. And that's like I guess it's a whole thing here, but I don't know, I was pretty happy with how I was able to just kind of throw something together with raw draw. And now the idea is that if you just print a bunch of values on lines, such as this, just values in a row, this tool can automatically take those and plot them in this sort of consistent way. And you can mouse over various fields and see what they're doing. One of the things I would still be really curious about is why, if anybody understands why some things, like this tool here, causes this weird pinching behavior. Like what kind of material is this that would cause it? If you know, please just let me know. I had a lot of fun doing this little project, and it was all based off of a little nerd snipe that happened earlier in this week by my friend Hikari Faith. So I hope you guys thought it was interesting as I thought it was, and yeah, thanks for watching.